All right, in this third part of chapter 7, we're dealing with sampling means. And so we're dealing with sampling distributions, but we're dealing with it in sample means. The last section we did sample proportions, but now we're looking at data that is looking at the means and sampling data from a population and calculating the mean or X sample mean or X bar. And then what we'll do is we'll look at what the sampling distributions look like and then do some probability calculations as well. All right, so let's look at the sampling distribution of the sample mean or the sampling distribution of X bar. So the mean is probably one of the most used statistics that we use in statistics. And so let's look at an example here. So on the left, we have a graph of all of the population for population data. So it's a population distribution of household earnings or household incomes. And of course, that's in thousands of dollars. So you can see that that is definitely skewed to the right, which makes sense. We get people, Bill Gates or whoever has incomes way out here, but there's not very many of those. And so that ends up skewing the data to the right. Now we take a sample of size 100 from that population, and so if we were to take a sample size of 100 many times, right, or all possible samples of size 100, so there would be lots of those, right? So if we could actually do a true sampling distribution, more often than not, we do a computer simulation with an approximate sampling distribution. So let's just assume that the one on the right is the sampling distribution from samples of size 100. Again, many samples, all of size 100, and we took each of those X bars and we plotted them. So you can see that the distribution is quite different. So the distribution appears to be normalish, certainly more normal than the original distribution. And so under certain circumstances, regardless of what the population distribution is going to be, the sampling distribution could still be considered normal, all right, even if the population is not. Now, what we're going to talk about first in this part of the section is let's assume that the population distribution is normal, and then we'll know, and we'll verify that, we'll know that the sampling distribution of X bar is normal if the population distribution of mu is normal. Then we know that the sampling distribution will be normal as well. And that's what we're going to talk about here really in this first section. All right, so when we choose a simple random sample from a population, the sampling distribution of the sample mean or X bar is always centered at the population mean. Now we know this because population mean, mu, because X bar is an unbiased estimator, and we talked about this in earlier in this chapter. All right, it's less spread out than the population distribution, and we can kind of see, if we look at the formulas, we can see why. So the mean of the sampling distribution will be equal to the population mu value from the population, and the standard deviation, that's going to be equal to this formula. And you can notice that the square root of n, which is our sample size, is on the bottom. So the bigger the n is, right? If we were just going to sample one, then we really wouldn't call it a sample distribution. We would just be the distribution would be the population distribution, and so the standard deviation of the sampling distribution would simply just be sigma. But when we sample, we're going to sample more than one. So you can see that the sampling distribution of X bar, right, which is this, will be the population standard deviation divided by the square root of n. So the standard deviation of the sampling distribution will always be smaller than the population standard deviation. All right, and then of course we always have to check before we even calculate the standard deviations. We need to check that the 10% condition is satisfied, that we're not sampling more than 10% of the population. All right, now what's interesting is that these rules about what the mean and what the standard deviation are always true, regardless of the shape of our sampling distribution. So often we're going to be able to determine that our sampling distribution is normal. But even when our sampling distribution is not normal, and we'll see when it is and when it isn't as we go through this section, even when it's not normal, the mean of the sampling distribution will still be mu, the population mean, and the standard deviation of the sampling distribution will still be the population standard deviation divided by the square root of n. So regardless of whether or not the sampling distribution is normal, these two formulas are still true. All right, this is a sort of homage to, this slide is paying homage to a particular professor at Rice University who developed a web-based sort of applet that we're going to play around with. When you look at your PDF of these notes, you'll see this button here, and it should be active. This button will work when you look at the electronic version of these, the PDF of these notes. And so what it does is it opens up an applet, and so I'm going to do that now, and then we'll talk about, and I'll work through with you that applet so that you can sort of discover that, I'll just talk about it here quickly before I move over. But the first distribution that they show in this applet is the population distribution, and that is clearly normal. And then what we do is we look at taking a sample. So it will actually animate and will take a sample for you if you hit the animation button over here. And then hit the animation button. But you have to set these up first down here. You have to set up your mean and your sample size. Now, it will animate this, and then this will be your sample distribution or distribution of your sample. And then the third thing down here is we're building up the sampling distribution. Now, in reality, it will be the approximate sampling distribution. And so this applet allows us to say, okay, here's the population distribution. As I sample from that population, what will my approximate sampling distribution look like? So click on that button, play around with this. I'll walk you through it right now. Okay, so once you click on the little begin button, it takes you to, you of course, hopefully you've done that on your PDF. Obviously, you wouldn't be able to do that if you printed it out, but on the PDFs of the PowerPoint slide notes, hit the button begin, and it takes you to this screen. All right, and then you hit the begin button over here. And so let me just explain what this website does. So it looks at the first normal curve looking distribution at the top is a population distribution. And so that's what we're exploring in this section, of course, is what happens when we sample from a population which is known to be normally distributed. And so this allows us to set up a couple different scenarios. So here I'm choosing the mean for the first case, and let's choose a sample size of 2. Now, I love this website, but the only thing that I would have changed is that the designer used capital N to denote the sample size. And of course, we we use a lowercase n to denote our sample size. Capital N should really be used to denote the population size. So that's the only criticism I have. Otherwise, this is a pretty good website. So look what happened. So I've set up, for right now, I'm going to leave this one down here as none. I don't want to work with this one. I'm just going to work with 3 distributions. So the population distribution, I set my sample size to 2, and we're looking for the mean. So I'm going to take a sample of 2 out of this population. So let's do that, and it sort of animates a little bit for us. All right, so I took a sample of size 2. So the first distribution is the population distribution, and then the second one here is the sample distribution, or distribution of a sample. And then the next one is what I'm going to eventually build up to be the sampling distribution. So we've done one sample, we've plotted that X bar down here, and then let's do another one. So sample another 2, and sample another 2, and sample another 2. So you can see that the X bars I get can be quite varied. I'm sampling 2, so most of the time the 2 are going to come from the middle of the population, but sometimes, like we saw for this one out here, they were both out here in the extreme. This one, they were both sort of to the left. Let's just sample, like that one, for example. I just by dumb luck got one way out here, very unlikely, but it happens. And so the average is pretty extreme. So I could just keep doing this. But of course, we don't have all day, so I'm going to instantly sample 100,000 of them. So I've sampled 9 so far. Well, let's just do one more. So I have 10, a sample size of 10. Hard to see what the approximate sampling distribution looks like with only 10. So let's jump to 100,000. All right. So you can see how the distribution of the sampling distribution looks. Now, again, this is not the sampling distribution. This is an approximate sampling distribution. Let's do another 100,000, another 100,000, another 100,000. So we have over now 500,000 samples in our approximate sampling distribution. Okay, so you can see if the population is normal, then the sampling distribution seems like it's going to be pretty normal too. And I can fit a normal curve to it. I can turn it on and off. So you can see how a normal curve fits to it. Now, before we go back to our PowerPoint, let's try one more thing. So let's turn on a different one. So let's do, our sample that we just did is a sample size 2. Let's turn on a second sampling distribution down below, and let's do a sample size of 25. So I'm going to leave my first one like I had, a sample size of 2, and this one's a sample size of 25. For each sample, I'm going to take 25. So let's animate. Now when I animate, it's going to sample 2, plot the resulting X bar down here, and then it will immediately start sampling 25 and plot that X bar down here. So those are my first 2, and now I'm sampling 25 for the second sampling distribution. All right, and so that was the X bar for that sample size of 25. This was the X bar for the sample size of 2. Let's do one more of those, and then I'll hit the 100,000 button. So here's my second sample of size 25. Notice that the sample distributions, since the sample sizes are pretty small, don't particularly have a normal distribution, right? You can't really see that they have a normal distribution. All right, now let's talk about how you can see how the X bars, I only have 2 of each, right? 2 for my sample size of 2 and 2 for my sample size of 25, but you can already see that the X bars for the samples of size 25 are much closer to the mean than the X bars for the sample size of 2. Now think about why that is. When we sample from the population, in order to get this one here, I would have to have 2 that are out here. So one would probably be more extreme than the other, but it's likely that I could get some X bars out here. Now, if I got an X bar out here, what would that have to be? That would have to have 2, when we sampled from the population, 2 observations that were sort of extreme. Not impossible, maybe not as likely as we would think, because they're more likely than not to be in this region here. However, think about what it would take for a sample size of 25 to have its X bar out here. That means all 25 observations would have to be extreme on one side, and that's not going to be very likely. So it makes sense just intuitively, if we see how we're sampling from this population, which is normally distributed, that we're going to see that the spread of the sampling distribution for a sample size that is large is going to be pretty small. The spread's going to be small, whereas if the sample size is small, then we're going to see that the spread is rather large. And we'll see why that is also with the formula. But let's hit 100,000. We did 2 for each. Let's instantly do 100,000, and you can see, let's go ahead and take it up to 500,000. All right, so this again is not a perfect sampling distribution, but it's an approximate sampling distribution with 500,000 samples. So that's pretty good. Now, you can see too, again, emphasize the fact that the spread of the sampling distribution from a sample of 25 is much smaller. The spread is much smaller than the spread that we got when we did a sample size of 2. And again, that's just because often we might get 2 values that are extreme on the left or the right, and that would give us X bars that are kind of out here. But it's very unlikely to get 25 in the second sampling distribution, 25 observations on one extreme or the other. So we don't see X bars. Remember, these are all the samples that we got, all 5, all 500,000 samples. None of them were out this way or this way. It's just much more unlikely. All right, we can also turn on our normal curves. You can see the normal curves fit pretty well through the tops of each one of those little bars. Okay, so let's go back to our PowerPoint now. Okay, so hopefully from the little web-based applet, we've kind of determined that the sampling distribution of X bar will be normal regardless of the size of our sampling, the size of our sample. So the sampling distribution of X bar is going to be normal, and it doesn't matter what the size of our sample is. So whether the sample size is large or small, the sampling distribution will be normal if we are sampling from a normal population. All right, and so that's kind of what hopefully you got from using that applet that we suggested you look at on the previous slide. Okay, so let's kind of pull it all together then. So what does this mean? That means basically 3 things. All right, if we are sampling from a population which is known to be normal, so we're taking it from a normal population, then we know that our sampling distribution, that's the distribution of all possible samples, will be normally distributed as well. Okay, now, regardless of the shape of our sampling distribution, we know that sampling distribution will have a mean equal to the population mean, and that's because X bar is an unbiased estimator. And then we also know, third thing, is that the standard deviation of the sampling distribution will be the population standard deviation divided by the square root of n. Now these last 2 things, dealing with the mean and the standard deviation, those 2, it does not matter what shape the sampling distribution is. The mean of the sampling distribution will be mu. The standard deviation of the sampling distribution will be sigma divided by the square root of n, regardless of the shape of that distribution. But we know that shape of that sampling distribution will, of course, be normal when the population from which we sampled is normal. All right, let's look at an example here. At the Peanut Company, dry roasted shelled peanuts are placed in jars by a machine. The distribution of weights in the jar is approximately normal. So that's telling us that the population distribution is normal. It's giving us a mean of 16.1 ounces and a standard deviation of 0.15 ounces. All right. Without doing any calculations, explain which outcome is more likely. Randomly selecting a single jar and finding that its contents weighs less than 16 ounces, or randomly selecting 10 jars and finding that the average content of those 10 jars is less than 16 ounces. All right, well, it makes sense. I think intuitively it's easier to find one jar that is less than 16 ounces than finding 10 jars with an average weight that's less than 16 ounces. All right, and we'll see in working through the next couple of examples, next part of this example, and we'll verify that, yes, this is true just by looking at our probability calculations. All right, so first let's look at an example. This is, we're randomly selecting one jar. So this is not a sampling distribution. This is the probability like we would have calculated in previous chapters. We know that the population from which we're taking one jar is normally distributed. And so what we want to think about is our 3 steps. We want to find the probability that one randomly selected jar is less than 16 ounces. So in step 1, we want to look at 3 parts. We want 3 parts to step 1, right? 3 components. And so what would those be? All right, so first we want to define a random variable. So X, let's say, is the weight of the contents of a randomly selected jar of peanuts. X has a roughly a normal distribution. They gave us the mean and the standard deviation. And we want to find the probability that X is less than 16. Now, you could have also said less than or equal to. That's the same thing. All right, part 2, step 2. We have 2 components to this. First thing we want to do is draw a normal curve. Shade it and labeled and shaded. So the mean is 16.1. We want to be below 16. So we shade to the left there. You can still use your z-score if you want, but I would recommend you using your technology, your normal CDF in this case. And then finally, the last thing you want to do is answer the question, essentially answering this third component of step 1 in the form of a sentence. All right, so there's about a 25% chance based on the value we got here, the probability, the area is the probability. So there's about a 25% chance or 25% probability that a single jar will contain less than 16 ounces of peanuts. All right, now in part C, we are sampling 10 jars. Okay, so now we're dealing with a sampling distribution, right? We are dealing with not the, the resulting p hat will fall within this sampling distribution. It will not fall, the 10, average of the 10 will not come from the population distribution. But now we have to think about it being a possible sample that would fall on the sampling distribution. All right, so first thing we want to do, again, we use our 3 steps here. Find the probability that a simple random sample of 10 jars contains less than 16 ounces. So we have a lot more than 3 components this time. There's a lot of things we need to check if we're looking at a sampling distribution for X bar. All right, so first, and no real particular order. Some things need to come before other things. So what I'm giving you here is a pretty good example of what you should be doing and in the order you should be doing. So what is it that we're looking for? Finding the probability that the average X bar for our sample of 10 is less than 16. All right, the second one, let's find the mean. All right, the mean of the sampling distribution will be equal to the mean of the original population distribution, and we know that because X bar is an unbiased estimator. We want to look at the what would the standard deviation of our sampling distribution be. But before we check that, we really need to check that we are not sampling more than 10% of our population. And so we can safely assume that the company is going to make more than 100 jars of peanuts. And so then and only then are we now allowed, since we checked our 10% condition, to calculate the standard deviation of the sampling distribution. All right, we want to talk about, okay, what is the distribution? What does the distribution look like for our sampling distribution? What is its shape? Is it normal, essentially? Because if it's not normal, we're kind of done. We can't do any normal probability calculations if it's not normal. And so indeed, yes, how do we know that the sampling distribution of X bar is roughly normal? And that's what you really want to say. You want to say those words, the sampling distribution of X bars is approximately or roughly normal. And how do we know that? We know that because the population is given to us as normal. So therefore, we know the sampling distribution of X bar is normal. The sample size does not matter in this case. It will later on, but for right now, it doesn't because we were given that the population distribution was normal. All right, and so then finally give what that population distribution is. So you can see when we do these sampling distributions, step 1 involves a lot of stuff, right? We've got to say what it is we're calculating. What is the mean? What is the standard deviation? But before we do that standard deviation, we have to check our 10% condition. We have to say what shape the sampling distribution is, or more importantly, we have to say that it's a normal distribution, because if it's not normal, we can't really proceed. And then also, just besides saying that it's normal, give what it actually is. So mean, it's normal with a mean of 16.1 and the standard deviation that we calculated in part 4 of 0.047. All right, now we can do our actual calculation work. This is going to, step 2 involves, first of all, drawing a normal curve labeled and shaded, and then doing the actual calculation. Again, you could use a z-score, or again, I would suggest just using your normal CDF in your calculator. Remember to put your lower, your upper, your mu, and your sigma, telling me that you know what those things are. And that gives us about a 1.7% probability. And so finally, step 3, answer that question. Now I've numbered all of these so you can kind of see 1 through 9 how many different components are required for these 3-step problems when we're dealing with a sampling distribution of X bar. So an open-ended question like this on the test would have a similar requirement. You would really need to have all 9 components. An open-ended test question like this would be worth 9 points. So it's worth quite a bit. I mean, this question is worth potentially about as much as all the multiple choice, and it's not that difficult. So make sure that you're learning and memorizing all the different components that you need when you go to do these problems, and practice that when you do your homework. If you're not practicing it in the homework, you're going to lose really simple points on your next assessment. All right, speaking of the homework, number 53 has, I don't remember part A, part B, but it has 2 different parts that require each 3 steps. So for homework tonight, even though there's 4 problems, there are 4 3-step components to this. So make sure that you're doing 2 parts in 53 and 2 parts in 55 using your 3 steps. So about 4 3-step problems in tonight's homework.